Hello everyone, welcome to the video lecture of this course Finite Element Method. So this is the fourth lecture of the first module of this course. So in the last lecture we have discussed the weighted residual method and we have solved some numericals based on the concept of this weighted residual method. So there we have seen the different weighted residual method like the point collocation, subdomain collocation, then least square method and the Galerkin method, and how to solve different numericals based on the different formulas of this weighted residual method. So today we'll be discussing the Rayleigh Ritz method. It is also one of the most important method regarding this finite element analysis. So it is one of the approximation method, a variational approach it is there. So today we will discuss the Rayleigh Ritz method, the different steps of this Rayleigh Ritz methods. There are actually 7 different steps of this Rayleigh Ritz method. So we will discuss those in details, and after that we will solve one numerical based on the concept and the procedure of this Rayleigh Ritz method. Okay, so let us start this lecture. So this Rayleigh Ritz method, it is actually an integral approach method and it is useful for solving structural mechanics problems. It is also known as variational approach. Now in this method we need to find the total potential energy, and the formula to find the total potential energy, this is denoted by pi. It is actually the strain energy minus work done by external forces. So the formula of this total potential energy, it is U minus H, capital U minus capital H. So this formula will be required to solve the numericals based on the Rayleigh Ritz method. Pi equals to U minus H. It is potential energy, this is equals to strain energy minus work done by external forces. Now in this Rayleigh Ritz method, there is an approximate function or approximation function, so it should satisfy the geometric boundary condition. Next, it should have at least one Rayleigh Ritz parameter and it should represented as either polynomial or trigonometrical. So what does that mean? So there are actually 7 different steps to solve the problems using the Rayleigh Ritz method. So what are the 7 different steps? The step number 1, it is as setting an approximation function. So this is our first step. We need to set up an approximation function. So it was actually written here that it should be represented as either polynomial or trigonometrical. These are the characteristics of the Rayleigh Ritz approximation function, that this approximation function, it should be either polynomial or trigonometrical, and it should have at least one Rayleigh Ritz parameter, and it should satisfy the geometric boundary condition. So these three are the characteristics of the approximation function which we will use as a step number 1 for this Rayleigh Ritz method. Now the step 2 will be to determine the strain energy U. So this is the step 2, that we need to determine the strain energy, which is denoted by capital U. Next, the step 3 is to determine the work done by external force. This is capital H. So the step 3, it is we need to determine the work done by the external force, which is capital H. Next, the step 4, it is to calculate the total potential energy, which is pi. This is equals to U minus H. Now this U will be determined in second step and this H will be determined in third step. So fourth step will be this U minus H, that is the subtraction of the value of step 3 from step 2. Next, in step 5, we have to find the Ritz parameter by partial differentiation. After that, in step 6, we need to determine the deflection for beam element and determine the displacement for bar element. So these are the two different steps in the step 6, that we need to determine the deflection of beam element and we need to determine the displacement for bar element. Next, the last step we are having, that we need to determine the bending moment for beam element and the determination of the stress for bar element also need to be done. So these are the 7 different steps that we need to remember to solve different numericals based on this Rayleigh Ritz method. Now let us discuss one numerical based on this Rayleigh Ritz method. The question which is given here, a simply supported beam, it is subjected to uniformly distributed load over entire span. So it is also visible in the diagram, that is W per unit length, that uniformly distributed load or UDL, it is given here. This UDL is acting over the entire span of that simply supported beam. Now we need to determine the bending moment and deflection at mid span by using the Rayleigh Ritz method. So this is the question given here. UDL is acting on a beam, a simply supported beam, the beam AB, it is given here in this diagram. At A x equals to 0 and at B x equals to L, and the total length of the beam, it is small l. The UDL which is acting here, it is W per unit length, and we need to determine the bending moment and deflection at mid span of the beam by using the Rayleigh Ritz method. So what was the step 1 here? The step 1 is to setting up an approximation function for beam. So first, the step 1, it is to set up an approximation function. And depending on the beam or bar, that approximation function, it should be polynomial or trigonometrical. So in case of this beam, it is a trigonometrical approximation function. So that formula of this approximation function, or the mathematical representation of this approximation function, it is y equals to a1 sine pi x by l plus a2 sine 3 pi x by l. So this is the first step here. Next, we need to find the value of the strain energy that we have seen here, that we need to determine the strain energy, that is capital U. Now the formula to determine the strain energy, this is capital U, actually EI divided by 2 integration 0 to L d2y dx2 whole square dx. So here we need to do the second order differentiation of the approximation function. After that, we need to put that second order differentiation here, and we need to do the square of that second of that approximation function. After that, we need to do the integration within the limit 0 to L. So this is a very lengthy process, and after solving these different steps, we will get the value of the strain energy U. This is actually EI pi to the power 4 by 4 L cube into A1 square plus 81 A2 square. So this will be the final value of the strain energy capital U. Next, the step 3 was to find the work done by the external forces, that is capital H. Now the formula for this capital H, this is actually integration 0 to 1 omega y dx. Now we need to put the value of the approximation function y here, and after doing the integration part, after several steps, we will get the final value of this capital H. This is 2 omega L by pi into a1 plus a2 by 3. So next we are having the fourth step, that is the total potential energy pi. We need to calculate. It is U minus H. So U we have calculated in second step, and this H we have calculated in third step. So this will be the mathematical representation now in the fourth step. This is pi equals to U minus H. Next, we need to find the Rayleigh Ritz parameter by partial differentiation. So this Rayleigh Ritz parameter, these were there in this approximation function in the form of a1 and a2. So these two parameters we need to find in step 5. So for that we need to do this part, that is del pi del a1 this is equals to 0 and del pi del a2 this is equals to 0. Now the value of this pi, this is here, this is the mathematical representation of the pi. So this del pi del a1 this will be equals to 0, again the del pi del a2 this will be equals to 0. If we do this differentiation, partial differentiation, then after several steps we will get the value of this a1 as 4 omega L to the power 4 by ei pi to the power 5, and the value of a2 this will be 4 omega L to the power 4 divided by 243 ei pi to the power 5. So this is the procedure to implement the step 5, where we need to find the Ritz parameter by partial differentiation. Now if we put this value of a1 and a2 in the approximation function, then the representation will be like this. That means 4 omega L to the power 4 by ei pi to the power 5 sine pi x by L plus the value of a2, that means 4 omega L to the power 4 by 243 ei pi to the power 5 into sine 3 pi x by L. So after putting the value of a1 and a2 in the approximation function, this is the mathematical representation of y now. Now we need to perform the step 6, that is the maximum deflection. So we need to substitute x equals to L by 2 in the representation of y. So if we put this value of x equals to L by 2 in y that we got in step 5, then after several steps we will get y max, this is equals to 0.013 into omega L to the power 4 by ei. So this is the procedure for the step 6, and the step 7 we need to find the maximum bending moment. Okay, so here you can see in the step 7 it is given we need to determine the bending moment for beam element and determine stress for bar element. But in this numerical, as it is given as the beam element, so that's why in step 6 we have determined the deflection in the beam element, and in the step 7 we need to determine the bending moment for the beam element, because this numerical is dealing with the beam element only. So in the step 7 we need to determine the maximum bending moment, and for the formula for maximum bending moment, it is actually known to us. We have studied in solid mechanics or the strength of materials. So m equals to ei d2y dx2. If we put the value of y here, then after several steps we will get m max, this is equals to minus 0.124 omega square. So this is the procedure of the Rayleigh Ritz method, considering one example. That several steps, several lengthy steps we have skipped here. We have just discussed in brief the several steps for the Rayleigh Ritz method. Now let us discuss in details the Rayleigh Ritz method, considering one example. The question it is given, we need to determine the expression for the deflection and bending moment in a simply supported beam subjected to uniformly distributed load over the entire span. So find the deflection and moment at mid-span and compare with exact solution using Rayleigh Ritz method. Now the approximation function, it is given here y equals to a1 sine pi x by L plus a2 sine 3 pi x by L. Now here we need to find the deflection and bending moment at mid-span, and we need to compare with the exact solution. So 7 different steps for this beam element we need to perform here. So for this simply supported beam, the Fourier series, it is known to us y equals to summation n equals to 1 comma 3 up to infinity a1 sine n pi x by L is the approximation function. Now here in this numerical, the approximation function it is given, that is considering the first two term of this Fourier series, that is y equals to a1 sine pi x by L plus a2 sine 3 pi x by L, where a1 and a2, these are the Ritz parameter. So this is the first step that we have discussed here to the approximation function consideration, which is actually given here in this numerical. If it is not given, then from this Fourier series we need to determine and we need to identify the approximation function for this beam element, considering the two different Ritz parameter. Now in the second step, actually we need to find the strain energy, that is capital U, and in the third step we need to find the work done by external force, and in the fourth step, this is actually we need to find the total potential energy, that is pi equals to U minus H. So this equation number 2, it is actually the fourth step, that is pi equals to U minus H. To get the value of pi, we need to find and we need to solve the second and third step. So to calculate the value of strain energy in the second step, we have seen the formula, that is EI divided by 2 integration 0 to L d2y dx2 whole square dx. Now in the equation number 1, we can see that y is given a1 sine pi x by L plus a2 sine 3 pi x by L. So from this equation number 1, we need to find the second order differentiation, that is dy dx. It is now a1 cos pi x by L, because it is given here sine pi x by L. So the first order differentiation for the sine pi x by L, it will be cos pi x by L. After that, for the term pi x by L, there will be one more part, that is only pi by L. So after that, for the second part of this equation number 1 in the right hand side, we will get a2 cos 3 pi x by L multiplied by 3 pi by L. So we can rearrange and write this dy dx as a1 pi by L cos pi x by L plus a2 3 pi by L cos 3 pi x by L. Now if we need to do the second order differentiation, then it will be minus a1 pi by L into sine pi x by L into pi by L minus a2 3 pi by L sine 3 pi x by L into 3 pi by L. So that means we are getting the value of d2y dx2. This is actually minus a1 pi square by L square sine pi x by L minus a2 9 pi square by L square into sine 3 pi x by L. So this is our equation number 4. So this value of d2y dx2 that we have got by second order differentiation of the approximation function, that we need to put now in the formula of the strain energy U. So if we put this value here d2 by dx2 in this formula of strain energy in the second step, so U equals to EI by 2 integration 0 to L minus a1 pi square by L square into sine pi x by L minus a to 9 pi square by L square into sine 3 pi x by L whole square dx. So this is the mathematical representation now of the second step. So as this is whole square, so we can write, taking this common pi and L. So if we take this common, and then we can rearrange this line and we can write ei by 2 into pi to the power 4 by L to the power 4 integration 0 to L a1 sine pi x by L plus 9 a2 sine 3 pi x by L whole square dx. Now we need to do the square of this a plus b whole square relation, that is a square plus 2ab plus b square. So we need to write in this manner. So ei by 2 into pi to the power 4 by L to the power 4 integration 0 to L. The first part, it is a1 square sine square pi x by L. Then the b square, it will be 81 a2 square sine square 3 pi x by L. Plus we are having 2ab, that means a is here a1 sine pi x by L and b is 9 a2 sine 3 pi x by L. So then dx. So that means this is our equation number 5 here. After that, here we are having three different parts within the integration. So separately we need to do the integration for these three different parts. So how to do that? Let us consider the first part, integration 0 to L a1 square sine square pi x by L dx. So this is the first part of this right hand side of the equation number 5 within the integration. So that means a1 square, it is constant, so a1 square, then integration 0 to L sine square pi x by L dx. So the formula of the sine square x, this is equals to 1 minus cos half 1 minus cos 2x. So these things we have studied while studying the calculus in our school level. So this formula of sine square x is equals to 1 minus cos 2x by 2. Okay, so this is now half 1 minus cos 2 pi x by L dx. So a1 square by 2 integration 0 to L 1 minus cos 2 pi x by L into dx. Now after that, next line will be a1 square by 2 integration 0 to L dx minus integration 0 to L cos 2 pi x by L dx. So this is the next line here. Next we need to do the integration here, that is for x, for dx it was earlier integration 0 to L dx, so that means it will be x and the limit will be 0 to L. And in case of the second part, that is cos 2 pi x by L, it will be sine 2 pi x by L divided by 2 pi by L. The limit is 0 to L. Now if we put the limit of the integration, then first we will write that L minus 0, and for the second part it will be L by 2 pi, then sine 2 pi L by L minus sine 0. Now as we know that sine 2 pi equals to 0 and sine 0 is also 0, so that's why we can write that L minus L by 2 pi within bracket, it is total 0. So that means ultimately we are getting a1 square L by 2. So that means the integration of this first part, that is integration 0 to L a1 square sine square pi x by L dx. So this is actually a1 square by L, a1 square L by 2. So this is our equation number 6 which we are getting here. Next, we need to find the integration of 0 to L, that is 81 a2 square sine square 3 pi x by L. Now here also if we do the integration, then using the similar procedure we can find the integration here. So that means after several steps we are getting the final value of this integration, and that means we are getting that integration 0 to L 81 a2 square sine square 3 pi x by L dx. This is we are getting as 81 a2 square L by 2. So this is our equation number 7. So next we need to do the integration for this part, that is the third part, that is actually was 2ab part of this a plus b whole square. So this is integration 0 to L 18 a1 a2 sine pi x by L and to sine 3 pi x by L. So here also we can do the integration which is shown here in several steps. There we need to use this formula, that is sin a sin b equals to cos a minus b minus cos a plus b divided by 2. So this formula we had to use here, and after several steps we have found the value of this integration, that is actually 0. So that means what? If we put this value of this separate of these three different integration in the equation number 5 of strain energy, then we are getting the final value of the strain energy, that is ei pi to the power 4 by 4l cube into a1 square plus 81 a2 square, so which is equation number 9. So this is the completion of the step 2 here. Next we need to find, in step 3 we need to find the value of the work done by external force, which is y. H equals to integration 0 to L omega y dx. So here we need to put the value of this y, that is the approximation function, which is a1 sin pi x by L plus a2 sin 3 pi x by L to dx. Now here also if we do the integration, then for sin pi x by L it will be minus cos pi x by L. So this thing it is known to us. No, so after several steps, after putting the integration limit and putting the value of cos 0 as 1, cos pi as minus 1 and cos 3 pi as also minus 1. So after several steps we are getting the value of this work done, h equals to 2 omega L divided by pi into a1 plus a2 by 3. So this is the value or the equation for the step 3, which we are getting as equation as number 10. So that means in case of the step number 4, we need to find the total potential energy pi. This is equals to u minus h. So as we have calculated u and h as step number 2 and 3, so we can write this representation of the step u and h here. So that means pi will be ei pi to the power 4 by 4l cube into a1 square plus 81 a2 square minus 2 omega L by pi into a1 plus a2 by 3. So this is the completion of the step 4, where we have calculated the total potential energy pi. Now in the step 5 it was given that we need to perform the partial differentiation and we need to find the value of the Rayleigh Ritz parameter, which are a1 and a2 in this approximation function given in the numerical. So for that we need to follow this procedure, that is del pi del a1 this is equals to 0 and del pi del a2 this is equals to 0. Now the value of this, if we do this del pi del a1, then we are getting this part, that is ei pi to the power 4 by 4l3 into 2a1 minus 2 omega L by pi, this is equals to 0, because the part with respect to a2 this will be 0 here. This is constant with respect to a1. So that means from this step we are getting the value of the first Rayleigh Ritz parameter a1. This is equals to 4 omega L to the power 4 by ei pi to the power 5. Using this similar procedure, we can calculate the value of a2, the second Rayleigh Ritz parameter, which we are getting is 4 omega L to the power 4 by 243 ei pi to the power 5. Now as we know, the approximation function is given, that is a1 sin pi x by L plus a2 sin 3 pi x by L. Now if we put the value of this Rayleigh Ritz parameter a1 and a2, then we will be getting this equation number 12. Here we have entered the value of a1 and a2. Now in step number 6, we need to find the maximum deflection occurs at the mid-span. So at the mid-span, x equals to L by 2. If we put this x equals to L by 2 in the earlier equation, means in this equation number 12, we need to put the value of x equals to L by 2. So after several steps, we will get this value of y max. It is the maximum deflection value we are getting here, 0.0130 omega L to the power 4 by ei. So at the mid-span, this is the maximum deflection. Now, in case of the simply supported beam subjected to uniformly distributed load, the maximum deflection, it is actually 5 by 384 omega L to the power 4 by ei. So this is the value, it is actually known to us, but this 5 by 384, it is actually 0.130 omega L to the power 4 by ei. Now the same value we have got here by this analytical method. So that means from equation number 13 we have got this value, and this equation number 14, that is the exact solution, it is also the same value. That means what? The exact solution and the solution obtained by this Rayleigh Ritz method, these are same. In the seventh step, we need to calculate the bending moment at the mid-span. The formula for the bending moment, this is equals to m equals to ei d2y dx2. The value of d2y dx2, this is already known to us. Now in this equation of d2y dx2, we need to put the value of a1 and a2. Now in case of the maximum bending moment, x was equals to x is L by 2. So again in this mathematical representation of d2y dx2, we need to put x equals to L by 2. So after several steps, we are getting the value of d2y dx2, this is equals to minus 0.124 omega L square by ei. So that means the maximum bending moment at the center, this is equals to minus 0.124 omega L square. Now this negative sign is actually indicates the downward load, but from simply supported beam subjected to a uniformly distributed load, the maximum bending moment formula, this is actually omega L square by 8, which is actually 0.125 omega L square. So from this equation number 16 and 7, we are getting that the exact solution, which is equation number 17, and the solution obtained by this Rayleigh Ritz method, that is equation number 16, these are almost same. There is a difference of only 0.001. So this is very much negligible. Now if we want to get this exact value, then we need to take into consideration more terms in the Fourier series. Okay, so this is the procedure to solve such type of numerical based on the beam with the help of the Rayleigh Ritz method. We need to follow the 7 different steps of the Rayleigh Ritz method, and after doing this lengthy procedure, we will be able to find the deflection and the maximum bending moment for the given beam section. Okay, so this is the end for this lecture. In the next lecture, we will continue some more numericals based on this Rayleigh Ritz method. Okay, so let us end this lecture here.